Welcome back. Today I want to talk about the idea of being differentiable and what does a function look like and what's going to happen, some characteristics for it to be considered differentiable. The word differentiable means that the slope of the tangent line from the left and the right side is going to approach the same value. So if we look at the slopes at any given point on the left side versus the right side, they're going to come to that same value. Same thing when we talked about continuity. The values were coming together for it to be continuous. Well, now differentiability means those slopes are going to come together at the same point, the same value. When we talk about differentiability, we're looking for things to have a nice smooth curve. So we don't have any abrupt, sharp edges, any sharp turns, those sorts of things. So a function is not differentiable if the function is not continuous. It has that sharp turn, we also call it cusp, or an absolute value graph. Or we have a vertical tangent line, where the derivative is going to be undefined. So what is it going to look like graphically? Well, if we look here at point A, hopefully we see that we have an asymptote here at the value of point A. So we know that we're discontinuous. Since we're discontinuous here, we're not going to be differentiable at A. For B, we're coming up and we're getting very vertical here. It looks like at this point, we're going to have a vertical tangent line, which the slope is not going to be defined as well. As we work our way over, we have a nice smooth curve, but then coming from the left side of C, it looks like we're getting close to a zero slope, where between C and D we have a negative slope. So we're going closer to zero, and then abruptly we change to a negative. So it's not going to be differentiable here at C either. Same at D, we have a negative slope, and then abruptly we change to a positive slope. So we're not going to be differentiable there either. And again at E, we have a discontinuity, we have a jump discontinuity again. So we know that we're not going to be continuous. Since it's not continuous, it's not going to be differentiable. So we cannot find the derivative. So let's look at some algebra behind some of these. Oh, before we do that, if a function is differentiable, it has to be continuous. If a function is continuous, it does not have to be differentiable. If you remember back in geometry, they said all squares are rectangles, but not all rectangles are squares. Same thing here. If a function is differentiable, it must be continuous. If it's continuous, it does not have to be differentiable. So in order for us to find the derivative, it has to be a continuous function. So let's look here at a piecewise function I've made up, x plus 1 if x is less than 0, x to the third plus 1 if x is greater than 0. So we're talking about the differentiability at 0 to start. Is it differentiable? Well, we could graph this, but notice in our restrictions, we don't have anywhere that we're equal to 0. Since x is not equal to 0, so f of 0 is undefined, we know that that is the first rule of continuity. We have to have the value. So f of 0 is undefined, so we know it's going to be not differentiable at x equals 0 because it's not continuous. The function is not continuous. My penmanship is not great either today, is it? So it's not differentiable at x equals 0 because the function is not continuous. Where is it differentiable? Well, x plus 1, hopefully, remember that is a linear function, and we know linear functions are all differentiable, and x to the third plus 1 is differentiable anywhere on that function. So it will be differentiable on the interval of negative infinity to 0, union 0 to infinity. In example 2, we're going to throw at you a absolute value here. So we have the absolute value of x minus 1. Is it differentiable at 1? Why or why not? So you could graph this. The absolute value of x minus 1 is going to come in something like this. Hopefully we see that we have the slopes on the left side are not going to equal the same on the right side. We have a nice cusp here. So we have a sharp turn. What does that look like? If we recall, if we recall the definition of derivative and the alternative form that we talked about yesterday, f prime of 1. If I were to find f prime of 1, that would be the absolute value of x minus 1 minus f of 1. Plugging in our 1, we get 0, divided by x minus c, our c value, which is 1. So we're looking at a limit as x approaches 1. So we're looking at the limit of this. The limit as x goes to 1 of the absolute value of x minus 1 over x minus 1. Hopefully, again, lots of hopefuls today as well, isn't there? We remember what the graph of x, the absolute value of x minus 1 over x minus 1 looks like. Here at 1, we have this graph, and this graph down here at -1 and +1, and there at 1 as well. So we see that these two values don't come to each other. This is at -1, this is at +1. So the derivative from the positive side does not equal the derivative of the right side. So we say this is not differentiable at x equals 1 because the slope of the function is not the same from the right and left side of 1. You may even want to put in there that the slope on the left side or on the right side is a +1, and on the left side it's a -1. That'd be even a little more precise of an answer. So where is it differentiable? Well, hopefully we see that it's always going to be -1 on the left side, always +1 on the right side. So it's going to be differentiable on the intervals of -infinity to 1, union 1 to infinity. And that's where we're going to be differentiable. I have one last example to throw at you, and here we're going to look at x to the 1/3. Is that function differentiable at x equals 0? Again, we can go ahead and use our alternative form, looking at f prime of 0. So that's the limit as x approaches 0 of x to the 1/3 minus 0 divided by x minus 0. Remember, we're plugging in our c values. Well, this gives the limit as x approaches 0 of x to the 1/3 over x. Simplifying that, we get 1 over x to the 2/3. If we were to plug 0 in, 1 over 0, that's undefined. We see that this is going to define a vertical tangent line. So if I were to graph x to the 1/3, the graph of x to the 1/3 comes in, comes up very, very strongly, and then goes out. So we see that we have a vertical tangent line at x equals 0. So we say that this is not differentiable at x equals 0 because there's a vertical tangent line. Vertical tangent line occurs at x equals 0. Okay, where is it going to be differentiable? Well, it's going to be differentiable. We have a nice smooth curve up to 0 and then out of 0. So it is differentiable on the intervals negative infinity to 0, union 0 to infinity. Hopefully that gives you an idea of what it means to be differentiable in some different cases on when we had differentiability versus not having differentiability. Good luck.